Hello, everyone. Welcome to our session on VHDL, an essential tool in the world of digital design and electronics. Today, we'll dive into the basics of this powerful hardware description language, its history, capabilities, and how it sets itself apart from other languages. Let's get started. Here's our agenda for today's session. We'll start with understanding what VHDL is and its role in hardware design. We'll take a brief look at its history, explore its major capabilities, and conclude with the concept of hardware abstraction in VHDL. VHDL stands for VHSIC Hardware Description Language, where VHSIC means Very High-Speed Integrated Circuits. It is a versatile language that models digital systems at different abstraction levels, from algorithms to gate-level implementations. What makes it unique is its amalgamation of sequential, concurrent, and timing constructs, which enables comprehensive system design, simulation, and verification. VHDL was born out of the VHSIC program initiated by the US Department of Defense in the early 1980s. The goal was to standardize hardware descriptions across companies to improve collaboration and reuse. In 1987, VHDL became an IEEE standard and later an ANSI standard, ensuring its wide adoption and compatibility. VHDL offers several capabilities that set it apart. It allows seamless exchange between chip vendors and CAD tools, supports hierarchical modeling, and is technology independent, meaning the same model can be used across different platforms. Additionally, it supports both synchronous and asynchronous timing models, making it versatile for various digital designs. VHDL unifies various description styles, structural, behavioral, and data flow, allowing designers to mix and match them as needed. It supports mixed-level modeling and enables test bench creation for verification within the same language. Its portability and readability make it a preferred choice for designers worldwide. VHDL models hardware devices using the concept of abstraction. Each device has an external view, defining its interface, and one or more internal views, representing its functionality or structure. This abstraction allows for flexibility in design and enables multiple representations of the same hardware device. First figure shows the hardware device and the corresponding software model. In VHDL, each device model is treated as a distinct representation of a unique device called an entity. Second figure shows the VHDL view of a hardware device that has multiple device models, with each device model representing one entity. Even though entity 1 through n represent n different entities from the VHDL point of view, in reality, they represent the same hardware device. The entity is thus a hardware abstraction of the actual hardware device. Each entity is described using one model that contains one external view and one or more internal views. These systems can range from something as simple as a logic gate to highly complex electronic architectures. The fundamental concept in VHDL is the entity. Think of an entity as a digital hardware module's abstraction. For instance, when an entity X is reused inside another entity Y, it becomes a component for entity Y. Essentially, a component is just an entity viewed at a different abstraction level. This modularity allows for scalable and hierarchical design in VHDL. In VHDL, describing a digital hardware module involves using design units. These units provide a structured way to define the system. Entity declaration defines the external view of the module, what it looks like from the outside. Architecture body provides the internal details, how the module works or how it is constructed. Configuration declaration helps connect an entity with a specific architecture useful during simulation or synthesis. Package declaration serves as a library for reusable definitions, such as constants and data types. Package body contains implementations of any functions or procedures declared in the package. These constructs allow for modular, reusable, and hierarchical design, which is the core of VHDL's power. Example: and gate in VHDL. Let's look at an example of an AND gate modeled in VHDL. The entity declaration defines the module as AND gate with two input ports A and B and one output port Y, all of type std_logic. The architecture body, labeled as behavioral, describes the functionality. The output Y is assigned the logical and of inputs A and B. This simple example demonstrates the seamless combination of an entity and its architecture to describe both the external and internal aspects of the hardware module. Every hardware component in VHDL is modeled using two main parts, the entity declaration and the architecture body. The entity declaration provides the external view of the entity, describing its interface, such as the input and output signal names. It acts like a contract that defines how other components can interact with this entity. The architecture body, on the other hand, defines the internal workings of the entity. This can include a structural description, which uses interconnected components to model the internal structure, a behavioral description, which employs sequential or concurrent statements to define the functionality, or even a combination of both approaches within the same architecture. This dual representation ensures that the design is both modular and scalable. Figure illustrates how an entity and its corresponding architecture model work together. To highlight some key points, every entity in VHDL requires at least one architecture body. However, it's not limited to just one. Multiple architecture bodies can exist for the same entity, each representing the design at different levels of abstraction or functionality. The flexibility in VHDL allows you to choose between a structural representation which focuses on component interconnections and a behavioral representation which describes the functionality directly using VHDL statements. This approach promotes reusability and modularity, making it easier to manage complex designs. Additionally, the ability to mix and match these representations fosters a hierarchical design process critical for large-scale digital systems. Configuration declarations in VHDL play a critical role in design management. They allow you to create configurations for an entity by specifying which architecture body to bind from the many that may exist for that entity. Additionally, configurations enable you to bind components within the selected architecture body to specific entities. This flexibility allows for multiple configurations of the same entity. For instance, you could select a behavioral architecture for simulation and a structural architecture for synthesis without altering the source code. Here's an example of a configuration declaration. In this example, the configuration, named my_config, is for the entity my_entity. The architecture behavioral is selected for this configuration. Within this architecture, all instances of component_name are bound to the entity other_entity, specifically using its structural architecture. This approach ensures precise control over how components and architectures are integrated into the design. A package declaration in VHDL encapsulates a set of related declarations, such as type declarations, subtypes, and subprograms. These declarations can be shared across multiple design units, enabling modularity and code reuse. A package body complements the package declaration by providing definitions for subprograms. This separation ensures that the interface and implementation are distinct, making the design easier to manage and maintain. By leveraging packages, you can enhance the readability of your code, ensure consistency across design units, and simplify debugging and updates. Let's explore an example of how entities, architectures, and bindings interact. In this case, entity E1 has three architectures, EI_A1, EI_A2, and EI_A3. For instance, EI_A1 is a purely behavioral model, while EI_A2 and EI_A3 incorporate components BX and CX, respectively. Similarly, entity E2 has architectures E2_A1 and E2_A2. The architecture E2_A1 uses component AMI. Entity E3 also has multiple architectures. The dashed lines in the figure represent configuration bindings. These include binding an architecture body to its entity and components within the architecture body to other entities. In a configuration, bindings define how architecture bodies and components are connected. Initially, E1_A3 is bound to entity E1 and its component CX is bound to entity E2. For entity E2 architecture, E2_A1 is selected and its component AMI is bound to entity E3. In an alternate configuration for entity E1, we can make these changes. Bind architecture E1_A to E1. Bind component BX within E1_A to entity E3. Use architecture E3_A1 for entity E3. This flexibility in configuration allows us to adapt designs for different scenarios without modifying the underlying source code. Once an entity has been modeled in VHDL, it must be validated using a VHDL system. The validation process typically involves two main components: the analyzer and the simulator. The analyzer reads one or more design units from a file, checks the syntax, and performs static semantic validation. Once validated, these design units are compiled and stored in the design library, a space in the host environment where the VHDL system keeps all compiled design units. Next, the simulator steps in to simulate the entity. It uses either an entity architecture pair or a configuration fetching its compiled description from the design library. The simulation process involves three critical steps: elaboration, initialization, and simulation. Each step ensures the correctness of the design before it is implemented. Once an entity is described in VHDL, the next step is validation. This is done through the analyzer and simulator. The analysis is the first step in the validation process. The analyzer takes a VHDL file containing one or more design units, such as an entity declaration, architecture body, or configuration. The analyzer compiles these design units into an intermediate form, validating the syntax and performing static semantic checks. During the analysis, the compiled intermediate form is stored in a design library. A design library is a specific location in the host environment where compiled descriptions are stored. Each design library has a logical name used in VHDL descriptions. The mapping of logical names to physical locations, such as directories and files, is handled externally by the host environment. The work library is always the working library, where the analyzer compiles the design units, ensuring only one library is updated at any time. The compilation process begins with the analyzer validating and compiling the design units into the designated working library. Even though multiple design libraries can exist at once, only one library is updated at any time, the work library. In a typical environment, a design library could be implemented as a directory in the host environment where the compiled design units are stored as files. When you need to store compiled descriptions in a design library other than the default work library, you can change the reference to work to point to the new library. The mapping between work and the design library is handled by the host environment. Furthermore, items compiled in one library can be imported into design units compiled in another library using the library and use context clauses. Alternatively, items can be directly selected to make them visible. VHDL has a predefined design library called std. This library contains two important packages. The standard package, which includes declarations for commonly used types in VHDL, such as bit, time, and integer. The TextShio package, which provides procedures and functions necessary for formatted ASCII read and write operations, allowing you to handle input and output with text files. Once the VHDL model description is successfully compiled into design libraries, the next step in validation is simulation. For a hierarchical entity to be simulated, all of its lowest level components must be described at the behavioral level. Simulation can be performed either on an entity declaration and an architecture body pair, or on a configuration. Before the actual simulation begins, two major steps must be completed: the elaboration phase and the initialization phase. Let's discuss these steps in detail in the next slide. The elaboration phase is the first step before simulation. In this phase, the hierarchy of the entity is expanded and linked. Components are bound to the appropriate entities in the design library. The top-level entity is built as a network of behavioral models ready for simulation. Additionally, storage is allocated for all data objects, such as signals, variables, and constants declared in the design units. Initial values are also assigned to these objects to ensure proper execution in the next steps. The initialization phase follows the elaboration phase. During this phase, effective values for all explicitly declared signals are computed, and implicit signals are assigned their initial values. Processes within the design are executed once until they suspend. Lastly, the simulation time is reset to 0, preparing the model for the actual simulation to begin. Once the initialization is complete, the actual simulation begins. The simulation advances time to the occurrence of the next event. Signals scheduled to be updated at the current simulation time are assigned their values. Processes sensitive to signal changes are executed until they suspend. The simulation halts when either a user-defined time limit is reached, an assertion violation occurs, or the maximum simulation time allowed by the VHDL language is reached. VHDL syntax has several user-friendly features. First, the language is case-insensitive. This means that names like carry, and carry all refer to the same identifier. Second, VHDL is free format, allowing designers to arrange their code flexibly, much like in ADA or Pascal programming languages. Finally, comments in VHDL begin with two consecutive dashes, --. Any text following these dashes on the same line is ignored by the analyzer, making it a useful tool for documentation and clarification in your code. To summarize, VHDL is a robust language born out of the need for standardization in digital design. Its ability to support various abstraction levels and integrate design, simulation, and verification makes it indispensable for modern electronics design.